Hello, chemists. It's Jolly again. All right, now that we've learned about the electrolytes and being able to do their equations, let's actually put them together and see if we can start predicting some reactions. So we are going to go to the notes, and I'm going to show you the three ways that we're going to write these equations or these reactions. And the first one is called molecular. Not really like molecular as a molecular compound, but what it's trying to show is that it is a complete formula unit or a complete molecular reaction. So everything is there. Okay, so it's all there. Nothing is missing. Ionic will show you which ones are actually floating around as ions. So it's the same equation, but it's telling you how they exist. And then the net ionic pretty much gets rid of the ones that aren't doing anything, and it only tells you who's important. And I don't want to say who's important. We'll just say active participant. The first one you should always write is the molecular, but the ionic and the net ionic can be very, very interesting and important as well. And we will come back to those. All right, let's talk about the types of reactions. In this particular section, we are going to talk about something called a metathesis reaction. It's also called a double displacement or a swapping reaction. It's a reaction which the parts swap, normally ions, but it doesn't have to be, to form the products. And it will always go to a lower energy state. Okay, so nature loves neutral or nature loves the lower energy state. And one way we can predict this is by, hey, solids or precipitation, those are generally more stable. Okay, so solids, gases, weak electrolytes, or non-electrolytes. Now remember, water is technically a weak electrolyte, but a lot of textbooks don't call it that way. So I put water right there as well. But remember, weak electrolytes and non-electrolytes. So a metathesis or a double displacement, we're going to swap partners. So I'm going to jump over to the whiteboard. All right, we are going to swap partners. So whatever I give you, so let's do a sodium chloride, and this time I'll say it's a solid, plus let's do some silver nitrate, aqueous. Now, this is the only type of reaction you really know right now, but we are going to look at the two pieces. So over here, I have the sodium and the chloride, and over here, I have the silver and the nitrate. Now, notice I don't care about how many of them I have, just that they're there. I am going to combine them. The sodium, the cation will go with the anion over here, and the cation over here will swap with the anion. And so this is what could happen. All right, so just do what could happen. All right, so I'm going to put my sodium with my nitrate, and I'm going to put my silver with my chloride. Now, I have to make correct formulas. So I have to trust their ionic information to be able to make it. So the sodium is a +1, the nitrate is a -1, so that's a correct formula. Don't touch the subscripts again. The silver in this case was a +1 because the nitrate was a -1. So I could trust the nitrate, so that means the silver had to be a +1, and silver is always +1. So one silver and one chloride also make it, okay? So I have correct formulas. So I'm going to swap and then make correct formulas. And now I'm going to balance. And in this case, it's going to be easy. One sodium, one chloride, one silver, and one nitrate. Okay, so in this case, it was a really easy balance. Then, okay, then I'm going to predict, oh, will it happen? Okay, so this is what could happen. will it happen? I need to look at, will it do something that's lower in energy? So 2. And I'm going to generically look for the formation of a solid, a gas, a weak, or a non-electrolyte. Ultimately, nature loves neutral and the lower energy state. We're just looking for basically phases. Well, how am I going to do that? So come over here. And our first question is it ionic or is it molecular? So this is ionic. Ionic comes in 2 forms. They're either soluble or they're insoluble. So soluble means they're floating around as ions, and insoluble means you'll see a precipitate or a solid form. So I go to my solubility rules, and all sodiums are ionic, so it's never going to form a precipitate. It's going to just float around as, oh, I didn't leave myself enough room, as aqueous. Okay, it's just going to float around as ions. All right, now I'm going to look at my silver chloride. All chlorides are soluble, except, now in this case, the silver is one of the excepts. So it is not going to float around 100% as ions. At least part of it will come out as a solid. And so did I form a solid, gas, weak, or non-electrolyte? And the answer in this case is yes. And so yes, it will proceed. So yes, it will happen. Right, let's try another. All right, let's see. Let's take some magnesium carbonate. And we'll take a bottle of solution off the shelf. But I want to react it with sodium sulfide. All right, step number 1. What could happen? Well, let's just swap the partners. So the magnesium is going to go with the sulfur, and the sodium is going to go with the carbonate. So we're just going to put those together. Doesn't matter which order I put them in, but yes, the cation has to come first. So order as in, do I put the magnesium first or the sodium? So magnesium with the S plus the sodium with the carbonate. All right, I've now put them together. I have to make correct formulas. Well, magnesium's a +2 and sulfur's a -2, so that one's correct. Sodium is a +1 and carbonate's a -2, so I'm going to need 2 to make the correct formula. Those are correct formulas. Don't touch them again. And now let's do the overall balancing. 1 magnesium, 1 magnesium, 1 carbonate, 1 carbonate, 2 sodiums, and 1 sulfur and 1 sulfur. All right, that's what could happen. Will it? I'm now looking for the formation of a solid, gas, weak, or non-electrolyte. So I'm looking over here, and I made an ionic compound, and I made an ionic compound. All right, ionics will either float around as ions or they will come out as a solid. So I'm going to my solubility rules. All sulfides are insoluble. Okay, it's at the bottom. All sulfides are insoluble, except, okay, this is not one of my excepts. So it's telling me it's insoluble, which means I put an S right there. I put an S right there. All right. All sodiums are soluble. End of statement. Or if you look at the bottom, all carbonates are insoluble, except, and sodium happens to be one of the excepts. So they're not going to form anything. They're just going to float around as ions. So I'll put an A, Q. And the big question, did I produce a solid, gas, weak, or non-electrolyte? And the answer is yes. So this reaction will proceed. This reaction will proceed. Let's do one more. Let's see. You know what? This time, let's make it a no. Let's take some sodium chloride, some table salt that was dissolved in the water, and let's react that with some calcium hydroxide. Okay, step number one. What could happen? Let's swap the partners. Sodium will go with the hydroxide. Calcium will go with the chloride. Calcium chloride plus sodium hydroxide. Now notice the subscripts, unless it's part of the polyatomic, you don't have to keep those subscripts. I'm making correct formulas here. So I've swapped them. Now I have to make correct. So calcium's a +2, chlorine's only a -1. So I'm going to have 2 of those. Sodium's a +1, hydroxide's a -1. So I'm fine there. So those are correct subscripts. Don't touch them again. Now I need to balance the whole thing. I have 1 sodium, 1 chloride. Oh, so I'm going to come back here and I'm going to put a 2. And in order to fix that, I'm going to put a 2 there. So 2 sodiums, 2 chlorides, 1 calcium, one calcium, and 2 hydroxides. That is the balanced equation. All right, that's what could happen. Will it? I'm looking for the formation of a solid, gas, weak, or non-electrolyte. So step number 1, oh look, I'm ionic. Oh look, I'm ionic. All right, I'm just looking for whether they're solids or not. I'm looking for precipitation. All calciums, okay, that one doesn't show up on your list. So you have to find one that does. So I'm going to go to the chlorine. All chlorides are soluble, except this is not one of the excepts. So it is aqueous, which means it's floating around as ions. All sodiums are soluble, end of statement. So this one's AQ. Did a reaction happen? No, I did not form a solid, gas, weak, or non-electrolyte. Something did happen, but it was not a reaction. All I did is the calcium hydroxide dissolved. There was no reaction. So, will it dissolve? Yes, but will a reaction happen? No, it won't. All right, that's the way you predict for precipitates, for the formation of solids. Let's go back to those equations. What is the difference between an ionic, a molecular, and a net ionic? Let me get rid of these. Nope. All right. This is a molecular equation. It has everything in it, and it's completely balanced. Everything's still put together the way it's supposed to be. All right. An ionic, it shows ions that are free, which means they're not attached in a solid. They're literally floating around in the solution. Well, how are you going to know that? Because they come from strong electrolytes. So what I'm asking is, are you really floating around as a magnesium carbonate, or are you floating around as a magnesium ion and as a carbonate ion? Okay, so that's what the ionic question is asking. All right, I don't remember what color it is, but in your reference sheet, it says net. It says net ionic. I'm on the. For me, it is underneath the circles that help convert between the grams, the moles, and the particles. All right, it says net ionic reactions. Okay, so this is exactly what I've been doing. Do the metathesis reaction, okay, figure out what could happen, then write the ionic equation using the solubility rules, okay, what will happen, and you're looking for the formation of a solid, gas, weak, or non-electrolyte. Cancel out all the spectators, blah, blah, blah. Okay, the little flow chart at the bottom. This is me trying to get into my ionic form. All right, and here's how we ask that question. All right, I'm looking at the left. I'm looking at magnesium carbonate. All right, first question. Are you aqueous? And the answer is yes. Next question. Are you ionic? The answer is yes. Basically, I just said I have ions floating around in water. What really is happening is, so I'm going to break them up. So the magnesium ion is floating around with the carbonate ion. So this is really how that is found. So the bottle that I took off the shelf, it was not solid magnesium carbonate. It was literally magnesium ions and carbonate ions floating around together. Okay, I'm going to ask the same question for the next species. Are you aqueous? The answer is yes. Are you ionic? The answer is yes. So you just told me that you're floating around as ions, not together. So I'm going to break that one up. Now notice the 2 goes in front of the sodium. Okay, not this. That doesn't exist. That is like the sodium metal. That doesn't exist. Okay, so no, 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 no. Don't write that. There's 2 sodium ions. All right, and there's also 1 sulfide ion. All right. All right, that is what this is. So I grabbed a bottle off the shelf and it wasn't solid sodium sulfide. It was literally a bottle that was carrying around 2 sodium ions for every 1 sulfide ion. Now remember, I'm the one that put the phase labels here. And so I had to ask myself, will those ions react together and give me anything? And let's go back to our first question. Are you aqueous? And the answer is no. So leave it alone. I actually made something. So I'm just going to rewrite this down here. So magnesium sulfide. Go on to the next one. Are you aqueous? Yes. Are you ionic? Yes. Really, you're just ions floating around. So 2 sodium ions plus a carbonate ion. Yep, I'm really running out of room right there. All right. So this is really what that is representing. Okay, it's not floating around as a solid. It literally is just the ions that are, attracted together. That is my ionic compound. It's telling me what's floating around. Now the net ionic equation, it gets rid of all spectators. Basically, the species that aren't doing anything, they're just floating around, taking up space. I'm so sorry. I started to cough and before I could mute it. All right, so that gets rid of all the spectators. If I'm doing that right, you can't hear me coughing or drinking water in your ear. All right, so let's look up here. Now they have to be exact. All right, there's 1 magnesium ion on the left, but this one is not a magnesium ion. I have 1 carbonate ion on the left and I have 1 on the right. So I'm going to cancel that out. I'm going to cough again. Sorry. All right, I have 2 sodiums on the left and I have 2 sodiums on the right. All right, and I have 1 sulfide on the left, but I don't have one on the right. So I bring everything that's left down. So my net ionic is the magnesium is really reacting with the sulfide to make magnesium sulfide. Okay, that's what's really happening because I've gotten rid of all the spectators. All right, so we have our molecular, shows everything. Our ionic shows us floating around as ions, and our net ionic tells us pretty much what's really happening. Okay, so that's how we do our molecular, our ionic, and our net ionic. That is completely different from saying will it happen? Okay, those are two completely different questions. Two completely different questions. One more example. All right, let's do, trying to remember the other one that I had. Well, we'll just make the new one. I'm going to take some zinc nitrate. And now I'm choosing what kind. I'm choosing that it's zinc +2, and I'm choosing that I'm going to go grab some solid off the shelf. And I'm going to react it with maybe some sulfate. So let's react that with some potassium sulfate. Again, I'm choosing the form and the kind, and I'm going to grab a bottle of it off the shelf in the aqueous form. And my question is, will they react? Okay, well, the first thing is, what could they do? So I'm going to swap. Zinc is going to go with sulfate, and the potassium is going to go with the nitrate. So I believe I could make zinc sulfate and potassium nitrate. Okay, so I've just combined them together. Now I have to make the correct formulas. And so zinc over here is a +2. So the zinc on the right-hand side has to be +2. Oh, and sulfate's a -2, so it's balanced correctly. The potassium is a +1 and the nitrate is a +1, so it's balanced correctly. So now I'm just going to balance it out as an equation. 1 zinc, 2 nitrates. So let's put a 2 right there. 2 nitrates, 2 nitrates, 2 potassiums, 2 potassiums, 1 sulfate, 1 sulfate. All right, it is balanced correctly. This is what could happen. This is what could happen. Will it happen? I'm looking for the formation of a solid, gas, weak, or non-electrolyte. So I'm looking over here. This is ionic. And this one's ionic. Ionics can either float around or they can make solids. So I'm asking myself, can you make a solid? So I'm looking at my solubility rules because it's ionic. And I can either look at the zinc or the sulfate, but there isn't one for zinc. So I have to go for the sulfate. All sulfates are soluble except, okay, all sulfates are soluble except silver, lead, calcium, strontium, mercurium-1, and barium. Zinc is not one of the exceptions. So guess what? AQ. Over here, all potassiums and all nitrates are soluble. End of statement. So guess what? It's AQ. Did I make a solid, gas, weak, or non-electrolyte? And the answer is no, I didn't. Okay, so there is no reaction. Basically, all I did was dissolve the zinc sulfate or the zinc nitrate. But let's see if the net ionic will tell me that. So no, there is no reaction. Okay, now that's the molecular formula. So the ionic formula, can I tell what was really floating around in my solution, in my beaker, in my test tube, whatever it was? And so I'm looking right here. Is it aqueous? No, leave it alone. All right, is it aqueous? Yes. Is it ionic? Yes, break it up. Now that 2, remember, means there's 2 potassium ions. And 1 sulfate. And yes, you do need to put the phase labels. All right, on the right-hand side. Are you aqueous? Yes. Are you ionic? Yes. Break it up, which means it's floating around as ions. Run out of room again. All right, are you aqueous? Yes. Are you ionic? Yes. Really, I'm floating around as ions. And I'll put it underneath. Notice there's 2 in front of the nitrate and 2 in front of the potassium. All right, that's what's floating around. Now I'm asking the question, well, what's really happening? Okay, that's the net ion. So I'm going to cancel everybody out that's the same. All right, there's 2 potassium iodides on the left, or sorry, not iodides, 2 potassiums on the left, 2 potassiums on the right. There is a sulfate on the left, there is a sulfate on the right. And so really, what am I doing? I'm taking zinc nitrate solid, And I'm taking it to the zinc ion and 2 nitrate ions. And if you'll notice, that's a dissociation equation. The only thing that's happening is it's dissolving. It doesn't even matter that it was potassium sulfate in there. It was just carrying, there was water. All right, that's the difference between a molecular and ionic and a net ionic reaction. And this was an example of the solids, the precipitate reactions. Okay, until next time, ciao, yeah.